Thanks for taking the time to watch this video. I wanted to make a note that if you are interested in any one-on-one tutoring, if you have an exam to prepare for, or a quiz, or some homework assignment that you're stuck on, I often meet with students via Google Meet for private tutoring sessions. So if you'd like more information about that, this is the best way to reach me right here at my email address, so feel free to drop me a line. You can also visit my website at wnytutor.com. Now for the solution. If you would like to, please pause the video just to reread the problem to get yourself reacquainted with what's going on here. In part A, we are asked, at what time does the particle momentarily stop? So of course, when a particle stops, then we know that its velocity is equal to 0. But in this problem, we are not given the velocity function. We are given a position function. But there is a nice way of changing a position function into a velocity function. And that is because the velocity is going to equal the derivative of your position function with respect to time. So what we need to do first is we need to calculate the derivative of our position function with respect to time. Our position function is 4.0 minus 6.0 t squared. And again, we're going to differentiate this with respect to time. Now, perhaps you've taken a calculus course and you know some of the basics of calculating derivatives. The derivative of the constant 4 is 0, so we would have 0. And then we subtract the derivative of the next term. Here you would use a power rule. So you would multiply the power by the coefficient. So 2 multiplied by 6 would give you 12. And then you subtract 1 from the power. So instead of t to the power of 2, you're going to have t to the power of 1. Now, when we simplify this, we can see that the velocity function is going to equal negative 12t. This question, again, wants to know when the particle stops. So what we're going to do is we're going to take our velocity, which is negative 12t, and we're going to set that equal to 0. Because when a particle stops, once again, its velocity is 0. Dividing both sides of this by negative 12, we can see that the time at which the particle stops will be 0 seconds. And so this is the correct answer to part A. In part B, we are asked, where does the particle stop? Now, a question of where would be a question of position. So we're going to look back at our position function, and recall that was x is equal to 4.0 minus 6t squared. We know when it stops, that was the time of 0 seconds. So all we need to do is plug 0 seconds in for the time. So we'll go ahead and do that, and when you simplify this, you would see that the position is equal to 4.0 meters. Let me just fix that. That should be a 0. So this is the correct answer to part B. In part C, we are asked, at what negative time and positive time does the particle pass through the origin? Okay, so through the origin, think about what the position of the particle would be if it were passing through the origin. And of course, the origin would be a position of x is equal to 0. So now we're going to take our position function and we're going to set that equal to 0. And to solve this for time, we could subtract 4 from both sides and then divide both sides by negative 6. We'll end up with t squared is equal to a positive 4/6 or 2/3. And then, of course, we need to take the square root. Now, when we square root this fraction, we're going to get both a positive and a negative root. And that makes sense because the question wanted both a positive and a negative time. And so for the negative time, which is part C, we can get approximately negative 0.82 seconds. And then for the positive time, which is part D, the time would just be the positive 0.82 seconds. So now we look at part E, and part E is asking us to graph the position versus time for time values between negative 5 and positive 5 seconds. So what we're going to do in this case is we're just going to find a grapher, and we're going to plug in this equation, but only on the interval from negative 5 to positive 5. So let's go ahead and see what that graph looks like. So here are the graphs. We just plug them into a graphing utility, and for part E, we have the original x function, and in part F, we have graph the function by including this plus 20t term. And that was part of what question F was asking us, whether we should include a minus 20t versus a plus 20t in order to shift the graph. You could play with that on your graphing utility. You would find that adding a plus 20t would shift the graph to the right. Now, there is one final part to the question. In part G, they want us to focus our attention again on when the particle stops. Now, look at the second graph, and to determine where on that graph the particle is stopping, you want to find a point on this curve where the slope is equal to 0. And why do we do that? Well, that's because the slope, and this is a very important point, the slope of a position versus time graph is going to equal the velocity. So we want the velocity to be 0 because the particle will be stopping. And if you look at this point right about here, and you drew a tangent line at that point, you can see that the slope of that tangent line is 0. It's kind of a flat line. The slope is 0 of that dashed line, and therefore the velocity is 0. You could do something similar on this graph as well. Right there, if we draw a horizontal tangent line, once again, at that point, the velocity would be 0. But now ask yourself, what's going on with the position? Here, the position, well, we actually calculated that. That was the 4 meters, and you can see that it's on the graph right there. But then look at the position here. If you kind of follow this over, you would see that the position is actually going to be a larger position. So the answer for part G is that the position is going to be a greater value than it was in the original part of the question. And so the final answer that we can display here is that the value of x at which the particle stops increases. And again, that's because the value on that x-axis right there is larger than the value on the x-axis on the original graph.